Hey everyone, so today we're talking about 2.8, solving inequalities in one variable. And essentially what we're trying to do is we'll be able to solve inequalities involving polynomials and rational functions using both algebraic and graphical techniques. And essentially we want to explore some of the common connections between inequalities and positive and negative signs of the expression. So something we've talked about before is that we got to remember that when we say f of x is greater than 0, we're saying that f of x is positive. And when we say that f of x is less than 0, f of x is negative. Now, I've been trying to stress that in class over and over again, so let's make sure we get used to this. Also, when we're going through this, we're going to see in the homeworks and just on the test that we're not going to be using positive and negative too much. So we got to get used to the symbols of less than and greater than for less than and greater than 0. So if I'm given this function, let f of x equal to x plus 3 times x minus 4 squared, and it says determine the real values of x that cause f of x to be 0, positive, and negative. So let's look at this as a problem that we've done in the past. If I want to make this equal to 0, that's just saying 0 equals to x plus 3 times x minus 4 squared. Well, it's already in our factored form. Our zeros are very straightforward. It should be x equals negative 3 and x equals 4. And what we have to do is figure out the positives and negatives. What we're going to do is use this number line, and it's something called a sign chart. And what we're going to do is we're going to put that on the number line. We know that negative 3 is smaller than negative 4. So we're going to put negative 3 over here. And we'll put positive 4 over here. And essentially what we're going to do is we just care about, is it going to be positive or negative in between negative 3 and 4, less than negative 3, and positive, above positive 4. So what we do is we plug in something less than negative 3. Well, the next obvious number is negative 4. So if I plug in f of negative 4, I get negative 4 plus 3 times negative 4 minus 4 squared. And we evaluate what the sign of this is going to be. Well, we know that negative 4 plus 3, well, negative 4 is larger than negative 3. We know we're going to get a negative here. And then if we plug in negative 4 minus 4, in this part, we actually will always get a positive number. Why will we always get a positive number? Because there's a squared here. Remember, negative 5 squared is the same as 5 squared. But here, as you realize, we get negative 4 minus 4. That becomes negative 8, but negative 8 squared gives us positive 64. So what we care about is that we get a positive sign here. So because of that, we know that we're going to get negative here on below anything less than negative 3. A value that we tested here was x equals negative 4. We can test a value in between, x equals 0. That's the easiest number between negative 3 and 4. And if I plug in 0 back into this, I get positive 3 minus 4 squared. So that's a positive times a positive, which gives us a positive. So we know so we're going to talk about what happens with the graph with this in a moment, but we know that between negative 3 and 4, the value of y is going to be positive. Now, if we take something greater than 4, okay, well, if we take something greater than 4, we plug it in here. Let's say x equals 5. That's the next easiest integer. We're going to have 5 plus 3. That gives us 8. That's going to give us a positive. And then 5 minus 4, which is 1. But like I said, because it's being squared, no matter what I plug into this parentheses, it's always going to be positive. So that's positive, and the result will give us positive. So we realize that anything basically larger than negative 3 is going to give us a positive value. All right. So this is a really good test for the sign of y. That's what we have here. Okay, so this is just a way to test out what will y be. And essentially what we're going to do is we're going to tie this into how we can graph this in the next example. Now, if I'm given the function r of x is equal to x plus 3 times x minus 5 over 2x minus 1, determine the real number values of x that cause r of x to be, well, we want to find out what causes it to be 0, undefined, positive, negative. This is a question that we've done in 2.6 for both part A and part B. We just haven't been asked this way. Well, think about it. What's another word for 0? The other word for 0 is x-intercepts. And I've asked you, how do we find the x-intercepts of this? Well, we make the numerator equal to 0. So we make x plus 3 times x minus 5 equal to 0. And what we find out is that we get x equals negative 3, x equals 5. Now the undefined. Well, undefined, we've also said this to be a vertical asymptote. So this is our vertical asymptote. And the way we find the vertical asymptote is we make the denominator equal to 0. So this will be 2x minus 1 is equal to 0. And we find out that x is equal to 1/2. Now for positive and negative, that's a little bit different. We have to use maybe a sign chart to help us figure out where we get the positive and negative. So a sign chart, what we always do on the sign chart is we put our zeros. I know I have negative 3 and I know I have positive 5. And we're going to do the exact same thing that we've done in the previous examples. In the previous example, on example 1, where we're going to test out some values. So let's test out x equals negative 4. And in between, let's test out x to be 0. And to the right of it, let's try out x equals 6. Okay, so we're going to plug this in and see what we get. Well, if I plug in negative 4 plus 3, I know I'm going to get a negative, because negative 4 plus 3 gives me negative 1. Negative 4 minus negative 5, that gets me another negative. That's going to all be divided by negative 4 times 2, which is negative 8, minus 1, that's another negative. So what happens here is, remember, a negative and a negative equals a positive, but then I get a positive over a negative, then I'm just going to get nothing but negatives on this part of the graph. So I'm going to put negative signs below my x equals 4. Now for x equals 0, this one's a little bit simpler. We can find out directly. I go, okay, if I plug in 0, I get 3. That gives me a positive. The other one gives me negative 5. That gives me a negative. And at the bottom, if I plug in 0, I get negative 1. So what we get here is positive and a negative gives me a negative. But a negative over a negative gives me a positive. So we put positive signs there, knowing that between negative 3 and 5, I'm positive. Less than negative 3, I'm negative. Now, a value that I did not include, then I should include, I apologize here, I should also include my undefined. There could be a change at my undefined. And I need to include also 1/2, my vertical asymptote. I apologize here. I should have my vertical asymptote. And there could be values there that are different. So I need to pick something that's larger than 1/2. We can pick 1. Plug in a 1 here into these and see what I get. Well, 1 plus 3 gives me a positive. So I get a positive. 1 minus 5 gives me a negative. And if I put a 1 here, 2 minus 1 gives me a positive. So what happens here is I get a positive times a negative over a positive, and that gives me a negative. So I'm going to get negative signs here. So negative signs are happening between 1/2 and 5. Now I got to test out first x to be 6. Now we could get a change here where this can become positive, or it might continue to be negative. Let's test it out. So we go back to the original function again. We plug in 6. 6 plus 3 gives me 9. That's a positive. I care about the sign. 6 minus 5 is 1. That gives me a positive. 6 times 2 is 12. 12 minus 1 is a positive. So I get nothing but positives here. If it's positive, 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 everything's positive. So after 5, we have positives. Remember, these are what the y values are going to be. That's what we said earlier. It's a test for the sign of y. So how does that graph work? Well, let's put our x-intercepts. We know that our x-intercepts are going to be at negative 3. We got an x-intercept there. We know we have an x-intercept at 5. So we put an x-intercept there. And we know we have a vertical asymptote at 1/2. So at 1/2, we're going to put a dotted vertical line and say x equals 1/2. And we're just going to do a nice little quick graph. Nothing too fancy. I'm not going to ask you to plug in any points. All we know is that everything before -3, the y value was negative. So I need a graph that goes negative down this way. But after 3 and between 1/2, everything's going positive. And we have an asymptote, so it should be hugging that line. So it's going to approach it and eventually hug that line like an asymptote. After that, after the 1/2, we get negative up to +5. So we're going to have something that's hugging this again, but then it's going to curve up to be up to the +5. Then after 5, everything is positive. So it's not coming back down. Instead, it's going to continue through 5 and go up. And we get a graph, something like that. Now, if we graph this on the actual graphing calculator, it might not, the curvature might not match it. I'm not really worried about that. I care about your sign chart, your graph, what you're telling me for 0 undefined. And now we can, using our graph and our sign chart, we can write intervals when things are positive and negative. So as we can see, positive is happening between -3 and 1/2. So we're going to write that just the way I just said it. It's going to be from -3 to 1/2. Remember, I'm saying from the small number to the big number. But we also have another situation where it's positive. It's up to 5 and every number after 5. So we do union 5, infinity. And there's our positive values. Negative happens when it's from every number less than -3. So that's going to be the negative infinity, -3. And we have a little negative between 1/2 and 5. So we say union 1/2, 5. And also we can even see that matches our graph. You see before -3, all our y values were negative. Between 1/2 and 5, all our values were negative. Likewise for our positives. Now in example 3, we are asked to solve a polynomial given that it's in an inequality format, right? So what we have here is that we have to do the same exact thing we've done before. We need to list out our P over Qs. Well, remember, our P's and Q's have to do with the constant over the lead coefficient. So we're going to say that the P's over Q's for this one is going to be ±1, ±2, ±3, and ±6. And in doing so, we're going to test out values doing division using synthetic or long division. In the interest of time, I have gone through this problem ahead of time, and I know that 2 is a 0. But what I would have done before that, and the way I did it before I did this video, was I tested out 1. I plugged it in. Did I get a remainder 0? I didn't. So that means that 1 was not a 0. I tried -1. I still didn't get a remainder of 0. Then I said, okay, I'm going to try out 2, and we're going to see how that works. So we get 1, -4, 1, and 6 for our coefficients. And do the the synthetic division. We bring down the 1. 1 times 2 is 2. -4 plus 2 is -2. -2 times 2 is -4. 1 plus -4 is -3. -3 times 2 gives me a -6. And sure enough, I got a remainder 0. Let's recall that this 1, this -2, -3 are the values to the quotient, and the powers are associated to each number, and we count up from the right to left, and we say, okay, this one's going to have an x to the power of 0, this is going to have an x to the power of 1, and x to the power of 2. So this is actually going to be x squared minus 2x minus 3 as the remaining quotient. And we're trying to solve, so we're trying to find the zeros of all this function. And since it's a quadratic, we can factor this very easily. And if it doesn't factor, we can also use the quadratic formula. But this factors to be x minus 3 times x plus 1. And this is equal to 0. And what we found out is that with these two factors, along with the 2 being a 0, we can write it in factored form as x minus 2 times x minus 3 times x plus 1, and that's equal to 0. And again, we're not really worried about the exact zeros just yet. What we're going to do here is figure out what all the values give us less than or equal to 0. So we're going to do a sign chart. Okay, so we want to do a sign chart. And we're going to put -1, 2, and 3. And here we want to find out if anything that is less than -1, if we'll get a true statement. Now, what makes a true statement? Well, it's saying whatever on this left side makes these values less than 0. So we want to get negatives. If we get negatives, we're going to call this true. If we don't, then we're going to call it false. So the best way to do it is not use the original equation. It's to actually use the it's to actually use the factored form to figure this out. So what I'm going to do is I'm going to use x equals -2. I plug in -2 here, and I get -2 minus 2. Well, that's negative. -2 minus 3, that's also negative. So a negative and negative give me a positive. Then I put in -2 plus 1. That's still negative. So I get a negative out of all this. And a negative means that it's less than 0. So I get a true statement here. So because it's true, this is part of my solution. But let's continue through here. Well, between -1 and 2, let's use x equals 0. I plug in 0. I'm going to have -2 times -3. That's going to be positive 6. Positive 6 times 1, that stays positive. I don't want a positive. Positive means that it's not less than 0. So then therefore I get a false statement. So we're going to put false here. Then I pick a value between 2 and 3. So here is sadly I got to use a fraction. I got to use 2.5, or I can say 5 halves, but I say x equals 2.5. I plug these into here, and what happens is that I get 2.5 minus 2. That's positive. Remember, I don't care what the exact number is. We don't care about that. So that's the nice thing about using decimals here. We just care about positive or negative. I plug in 2.5, I get positive, but I plug in 2.5 here, I get negative. 2.5 minus 3 is a negative because 3 is larger. And then 2.5 plus 1 is a positive. So I'll get a positive times a negative, which is negative, and then a negative times the positive, which stays negative. So, or excuse me, I have a positive times a negative, which is negative. Negative times the positive stays negative. And that means that I get a true statement here. I apologize for that. I wanted to make sure I was saying that correctly. So we got negative there. We plug in something larger than 3. We can plug in 4. 4 minus 2 is positive. 4 minus 3 is positive. 4 plus 1 is positive. Positive times positive times positive. We get positive here, and that's for when x equaled 4. And since we get positive here, we can say, okay, this is a false area. So our solutions are only where we get trues, where we got the negatives. Now, why is it negative? Because the question said less than or equal to 0. If it was saying greater than or equal to 0, this would be completely flipped. These would be our true statements. But since they're not, we go with this, and we say that our answer is going to be where the negatives exist. Well, it's everything less than -1. So we're going to say negative infinity, comma 1. We're including 1 because, or excuse me, -1, because -1 did give us equal to 0, right? Because that's one of our zeros. Then we're going to say union, and we know that the next true area is between 2 and 3, and we know 2 and 3 work because those are zeros of the function. So we can say that 2, 3 in brackets. And I just realized this up here should not be equal to 0, should be less than or equal to 0. All right, moving on to example 4. Example 4 is asking a very similar question. The only difference is now things aren't nicely laid out for us, but we're going to use the same approach of example 3 to do this problem. Now, the first things first is that we got to make sure that this is set in a format where 0 is on one side. So I'm going to add 8x, and I'm going to subtract 2 to both sides. Okay, so it's -2 and then -2. So what I get here is should be x to the 3rd power minus 6x squared plus 8x minus 2 is less than or equal to 0. We want something like this where it's set in the format of that. Now here, in order to get my zeros in this problem, we have to see if with P over Q's, if it works out. It does not work out. And if this was on the test, this would probably be on the graphing portion of the test where you'd get something there. But I'm not going to give you guys a function like that so difficult. So what I did was I used the graphing calculator, or I used Desmos. You can go on Desmos and check it out. And I just found my zeros through there. And I found out that one of my zeros is 0.325. Another one is 1.46. Another one is 4.214. These are the zeros I got from the graphing calculator. And like I said, we could also go on Desmos and find those zeros as well. And if you need to, I can show you that in class, no problem. So what I did was I just picked a value in between these and I plugged them into this original function. Well, I picked a value that would, remember, they're supposed to be less than or equal to 0. I picked a value that was smaller than 0.325, and I plugged it in and I got a negative answer. So what happens there is I say, okay, I got negatives here. This is a true statement. Then I found out after that, I picked a value between 0.325 and 1.46. Well, a nice number between those one is just 1. I can plug in 1 here. If I plug in 1, I find out that I get positive values. This is a false statement because remember, we want less than 0 or equal to 0. Then we pick another value between 1.46 and 4.21. Well, 2 is a nice number. You plug in 2. If you plug in 2, you find out you get negative values. And again, that negative means that we get a less than. So that's a true statement here. And I pick another number greater than 4.214. I put 5 in here. And I get a positive number. So I put in plus signs. And I say that this is false. Again, I didn't show the work for this, but all I did was, like I said, I picked a number less than 0.325. A nice easy number is 0. You plug in 0 here, you get 0, 0, 0. Negative 2 is less than 0. That's a true statement. We put negative signs. Here I picked a value of 1. I plug in 1 into all the x's, and I find out that I get a positive number. Here I put a value that was between 1.4 and 4.2, which is a nice number, is 2. Plug in the 2, I get less than 0. And then for 4.21, I picked a 5, and I plug in 5 in here. And we find out that that is greater than 0. So that's why I got a false statement. I just did not show the calculation, but you guys can put that in your calculators to verify, to see how I got this. Feel free. So I find out that my solution, or my solutions, exist in the intervals of negative infinity, because it's before this, from negative infinity to comma 0.325. Union with this interval of the negatives, and that's going to be bracket 1.461 comma 4.214. Again, how I got these numbers is I went on Desmos, or you can I use my graphing calculator, but you can also go on Desmos and just go where the x-intercepts are and click on it. It'll give you the x coordinates of that. So with that information, I can plot my graph. I can say, okay, well, 0.325 is somewhere here, and 1.46 is a little bit further ahead, and then 4.21 is a couple more units ahead. But based off this sign chart, I know that everything before this x-intercept of 0.325 is negative. So I can just go, okay, that's going down. I also know that everything between 0.325 and 1.46 is positive. So it's going to be some kind of curve like that going positive. Between 1.46 and 4.214 is going to be negative. So I want negative values. So it curves back up. And then after that, it's going to be positive. So I have it go straight up. And there's my graph. Nothing more to it. Very straightforward. I'm not, like I said, I'm not checking to see how high or how low you make these. You just got to make sure that they connect to the next intercept and you're showing that they're positive values and negative values. And that's all you have to do. If you have questions, please feel free to ask me in class. I have no problem answering those questions tomorrow in class. Example 5 is saying let f of x equal to x squared plus 4 times 3 minus 2x squared. Solve for the following. Okay. So here it's very similar to example 1, but now we're writing them with the greater thans and less thans. Remember, f of x is greater than 0 means when it's positive. That's just like example number 2, where I asked you positive, negative, undefined. This is the exact same question, but now we're not using the words. So I sure hope that you guys are going to be able to do these problems and not be like, whoa, why is this so different? So it's asking when it's positive. Well, let's look at what we have here. Remember, I told you if we have a squared on the outside, that whole quantity will forever be positive because no matter what number I plug into this x, yeah, the inside of the parentheses will be negative, but after I evaluate the parentheses, I always get a positive. Likewise, what happens here is that I have another situation where I have x squared plus 4. No matter what number I plug in for x, this x will always be positive. And because of that, these two parentheses will never be negative. But that's something you have to be very careful with the words I just used. I said they'll never be negative. I didn't say they can't be 0. So notice here that this is saying when it's greater than 0. So the answer that people would think is like, oh, well, you just said they both can't be negative. That means all real numbers. That's not true. Because yeah, x squared plus 4 can't equal 0, but 3 minus 2x can. So we can say 3 minus 2x is equal to 0. And what we find out is that x is going to be equal to 2/3. Or sorry, 3/2. So x equals 3/2. And because of that, that's when it's equal to 0. And here it's not equal to 0. So what we have to do is just state out that all the other numbers work in this situation. Everything's positive except for when x equals 3/2. And at x equals 3/2, it is 0. So we're going to say that negative infinity, comma, 3/2, or 1.5, whichever way you want to use it, union with 3/2, comma, infinity. That's all the numbers except for 3/2 are going to be considered positive. So that means in part B, if we have greater than or equal to, now this is where it's all real numbers because now we can include the 0 as well. So we're going to say, oh, that's negative infinity to positive infinity. Well, with that discussion, we just said everything is always positive. Well, what about when it's negative? Well, that means that it's no solution. Because we just said this can never be negative and this can never be negative because of that squared on the outside. Oh, but then D actually has an answer. Well, we got to be careful because it says there's an equal to 0. Well, the function can never be less than 0, but it can be equal to 0. So here we're just going to say x equals to 1.5 or x equals to 3/2. All right. Now, here we have two very interesting functions that aren't polynomials, but we can still use the same knowledge to really figure out what the answer is here. So here it's saying solve for when x is going to be equal to 2. X minus 2 times the square root of x plus 1 is less than or equal to 0. Well, we're just going to branch them out like we've done in the past. We're going to say x minus 2 is going to be less than or equal to 0. And we find out that x is less than or equal to 2. And we can do the square root of x plus 1 is less than or equal to 0. And how we solve this, well, we want to get x by itself. We need to square both sides. And what happens there is we get x plus 1 is less than or equal to 0. And then we say, okay, well, then x is going to be less than negative 1. Okay. Now, why did I get rid of the equal to? Well, because if I plug in, when I plug this in, it doesn't really matter about what's going on, but I can include it. It doesn't really matter because what happens is these two kind of overlap. This x is less than or equal to 2 is actually overriding this negative 1 because it's including more values. So what we have here is that we actually have to see what happens though if I made my x less than 1. Well, if I make my x less than 1, or negative 1, like say negative 2, I plug in negative 2 here. We got to do a sign chart. And if I plug in negative 1 and positive 2. Well, I know if I plug in 0, I get negative 2 and times the square root of 1. Well, negative 2 times 1 is going to be negative, so that's a true statement. So I know I'm going to get negatives here. But when I plug in something greater than 2, remember, we already see it here that it can't be that, but we got to still see it anyways. If I plug in, say, 3, well, if I put 3 minus 2, that's 1. But 3 plus 1 is going to be 4. Square root of 4, that's 2. 2 times 1 is going to be 2. That's greater than 0, so we get a false here. But what happens when x is less than negative 1? That's the interesting part. Now, let's say I plug in negative 2. Well, negative 2 minus 2 is negative 4. Well, that's fine. That works fine. But negative 2 plus 1, what happens there? Oh, let's look at it. Square root of negative 2 plus 1. And what happens here is I get the square root of negative 1, which equals I. And we just said earlier that if we get i's, we said this back in 2.6, we get i's, that means they're imaginary, they're undefined. We don't see it there. So we're going to put undefined, and we know that the answer doesn't exist here. So our final answer is we only have one section of true. So our final answer is negative 1, 2. And that's our final answer. Now, here we have an absolute value symbol. Now, we have to be very careful about the absolute value, but really what we only have to worry about here in this absolute value is concerning ourselves with what the graph happens. Well, what happens on the graph. Well, when x is 4, we get a 0 and we get some undefined. And that really is an issue. So we know that x cannot be 4. The other thing that we have to look into is just realize, when do we get negative values? Well, an absolute value will never be negative, right? Remember the absolute value of, let's say, negative 5? We said that that's 5. Remember, the absolute value can't be negative. So we know that this is not an issue. This is always going to be positive. That's going to help us get greater than 0. But this numerator is what determines when we get a positive or negative. And we want greater than or equal to 0. So we really only care about x plus 1 being greater than or equal to 0, because its denominator will always be positive. So this is really what the x values have to determine. So we get x is greater than or equal to negative 1. So as long as our x is greater than or equal to negative 1, we'll be fine here. But we also know that x cannot equal to 4. So we know that it needs to be greater than negative 1, but it can't be 4 because we get a 0 in the denominator when we have that. So now we can write our answer. Well, we know that we can have negative 1 to be the smallest number. It can go up to 4. It just can't include it. So we're not going to include 4. But we also want all the numbers after 4. So it's going to be 4, infinity. And that's our answer there. All right. So the last problem here, we're designing a box. And here we have a Florida Paper Products has a contract to begin to design a box with a volume of not more than 200 inches cubed. Squares are to be cut from the corners of a 15-inch by 18-inch piece of cardboard, with the flaps folded up to make an open box. What size squares should be cut from the cardboard? So what we got to do is, we know that we have a 15-inch by 18-inch. What means is that that's the width and the length of the box. That's not this whole piece. Remember, these dotted lines here are expressing how it's going to be folded up. So the box is like, if this is the box, we're going to fold it up and actually, put all the corners together and make a box out of it. So right now it's a flat piece of cardboard, but it's going to get folded up. So really where our 15 inches is going to be, our 15 inches is going to be, 15 inches is here, and our 18 inches are here. But we have to include these corners. These are corners that are being cut, but we have to first understand how much of it is being cut. So we have to say that from here to here is that this is going to be, or it's going to be some 18 minus 2x. How did I get 2x? Well, what I'm going to say is I'm going to call this distance from here to here. I'm going to call this distance x. And then I'm going to call this distance x as well. Well, if this whole thing here is 18, then and this is x and x, well, I'm taking 18 minus x minus x. That's the same thing as 18 minus 2x. Likewise, we said they're squares. So then that means that from the distance from here to here is 15. Or sorry, it's x, not 15. Sorry about that. And this distance from here to here is also x. I'm going to get 15 minus 2x for this spot here. Okay. So how do I go about doing this? Well, we set up an equation of 18 minus 2x times 15 minus 2x times x is less than or equal to 200. How did I get that? Well, remember, we're folding this up to be a box. So once we fold it up, the height of this box is going to be x, some length x. And the volume of any kind of rectangular prism is going to be the length times the width times the height. So my length is going to be the 18 minus 2x. My width is the 15 minus 2x. And my height is x. So that's my volume. And it tells us that we want the volume to be not more than 200. So I make it less than or equal to 200. I go about solving it. I get myself 18 minus 2x times 15 minus 2x times x. And I'm going to subtract the 200 over. So now it's going to be less than or equal to 0. I plug this. I can plug this into the calculator just like how we've done it before. And what I find out is that x, so my solution is the squares cut should be between 0, which is less than x, which is less than 0.95, and 5, which is less than or equal to x, less than or equal to 7.5. Now, I'm giving you just the solution for now because we're going to work on this one in class if needed. But I also want you to, I challenge you to go through this problem and figure it out. Go through here and solve for the x, FOIL it out if you need to, or you can also graph it and find out where it's equal to 0. But I also want you to try the algebraic approach. In class, we can do it together if needed. So let me know if you guys need help. But this is a 5. And I'll see you guys tomorrow.